Hi there, thank you so much for coming this evening. We're going to probably just start ahead, but people will be trickling in straight after lectures. As we said, it would start at 5. Welcome to this evening's Research Uncovered talk. We're nearly halfway through it. I think we are halfway through our series now. But this is the amazing talk on carbon electronics. Just before we start, though, I just want to talk a bit about the initiative. Research Uncovered is essentially an initiative to create a knowledge environment beyond what is the university and kind of give all students the access to world-class research at this university. So in the REF and the Research Excellence Framework, it was said that 98% of the research at the university is of international quality. So this initiative is very much about providing students with access to that research that isn't not just within the classroom, but beyond the classroom. So all the lectures are recorded, they go online, and they're available for all students to watch at any time. And they'll be up on our extragud/RU webpage. So, without further ado, I do have a little blurb for you, Sharon, but it is just taken off your website. So, Dr. Sharon Strawbridge is a senior lecturer in physics and astronomy, and her research interests lie in the area of nanotechnology and more specifically on the substance graphene and relative 2D materials, which we'll hear about today. She's a massive fan favourite with the students, nominated for various teaching awards, etc., and was also director of student engagement. So very excited for this afternoon's talk. And without further ado, we'll hand over to Dr. Sharon Strawbridge for Carbon Electronics Is the Future Black? Thank you very much.
Well, it's a fantastic opportunity for me to just talk about what I'm interested in. And anybody that knows me knows that I'm really keen on my particular area of science. I have a very broad interest in science in general, but all the way through, a common thread through everything that I've done for the last 20 years, carbon has popped up again and again and again. And a few years ago, about 7, 8 years ago, I started working with the graphene group, and I became very, very interested in a new material that promised a huge amount. And you can see by my choice of title, it's slightly ironic because I'd imagine that a lot of people here have heard about graphene, and it's been in all the papers, it's been on the radio, it's been fantastic, and it is a fantastic material, but I want to be really realistic with everybody about what at the moment carbon electronics can offer, but also looking ahead to think about what they actually can offer and the various permutations of using carbon in electronics can offer in the future. So the first thing I wanted to do is to give you some sort of sense of scale, because I think very often nanotechnology is a very difficult thing to put over to people because the scale and the size of things you're discussing is so small, it is very, very difficult to visualize what 10 to the minus 9 meters actually looks like. So I've found a very useful little diagram from a textbook, which I rather like. And the reason I rather like this diagram is it takes us from an ant. We can all imagine an ant. And an ant's probably about 5 millimeters long or so. You all know about meters, centimeters, millimeters. 1,000th of a millimeter is a micron or a micrometer, and then 1,000th of that is a nanometer. So it's a millionth of a meter. It's a very, very small quantity. So we've got the little ant there. Quite interestingly, if you come down to the level of a millimeter and below, you see a little dust mite. You can see some rather clever micro mechanics here, which also show what we can do mechanically at an incredibly tiny scale. But if we get much smaller than that, then all the molecular forces start to play a part, And there's a limit to how small we can make things move relative to one another before they start to stick up. Human hair down there. Come further down, about 2 to 4, 5 microns or micrometers. You've got your red blood cells. You can see that down a microscope. But still, that's very, very big in comparison with a nanometer. And this, a carbon nanotube, probably about a couple of nanometers across in diameter. So we're talking about incredibly, incredibly, incredibly tiny, 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 tiny proportion. We're down to the level of atoms and down to the level of electrons. Now, I don't know if anybody knows who this man is. He's Richard Feynman, and Richard Feynman was an incredibly forward-thinking and an incredibly clever physicist who won a Nobel Prize for work on electrodynamics, but that's not why I've got him up there. He was absolutely fascinated with the idea of being able to look at things at a minute scale. And he wrote an article and he gave a talk at the American Physical Society in 1959. It's an awfully long time ago. It's 56 years ago. And it was called There's Plenty of Room at the Bottom, because he'd started to describe what you could actually do. And to begin with, he thought about what people were capable of with all the technology that they had at their hands. And he offered this wonderful prize. $1,000 back then was a lot of money. It's like sort of £20,000 now. For somebody to come across and make a working electric motor that was about 1/64 of an inch, or 0.397 of a millimetre, or 397 microns, as we've just discovered, as a little cube. And he basically said he needed somebody to build an electric motor that fitted within that. Unfortunately, he was rather disappointed, as his letter says below, because the gentleman that actually managed to do it didn't use any new techniques whatsoever. He basically used some very, very clever and delicate engineering, but it was not at a really tiny scale. I've just explained about scale. We are literally magnitudes of difference between that and something of the size of a nanotube. And he was explaining how you could write the Lord's Prayer on the head of a pin, and how really that was the first tentative steps towards going down to that very, very tiny scale. And he really opened the floodgates to people thinking about what they could do. Now, I need somebody to hand some rather precious and very old items out. Would you like to hand these out? And then you can sort of pass them along. These are vacuum tubes. And there's a good reason why I have included these here. Because this large room full of these very, very smart gentlemen, they used to go to work in those days in their suits. And they were born middle-aged in those days, I've noticed as well. They were running the Colossus. This was a gigantic computer, and they didn't have transistors in those days, and they needed to control the flow of electrons, a current, and switch it on and off to perform what's called logic operations. And they used something called a vacuum tube, and I'm passing these around. Vacuum tube works really easily. And now you'll see what the fault in a vacuum tube is as it passes round. Do you remember the old-fashioned light bulbs before the LED ones? And once they'd been on for a while, what happened to them? They got really hot. I burnt my father's shed down with an old light bulb. That's a whole other story, but I did. I wanted to have a red light, and I wrapped a red rag around a light bulb, and I was trying to learn how to develop photographs. I was about 7 or 8 at the time, and I had the towering inferno. It was amazing. These things get hot as well because they basically involve a little tiny filament at the cathodic end, which is tungsten, and you heat it up with a current, and that boils off a little stream of electrons. That's your little electric, and you want to be able to control those electrons. So if you look carefully at this as it goes round, it has a little grid inside it, and there are various configurations of grids. But what they basically did was you allowed you to switch on and off currents of electrons and controllably do so, and amplify currents. They were used in telephone exchanges and things. Fantastically useful. Anybody that's got an old radio will know you had valves and things in them. And they were really useful, but they got hot. And several of the ones, I think a couple of the ones that are going round, you'll notice, have actually, they look a bit black because they've basically gone pop and the filament's gone on them. So these old valves were how they had to do it. These rooms got enormously, enormously hot. This has got the computing power, I suppose, of an electric toaster nowadays. It's just unbelievably, because each one of those, a little pair of these vacuum tubes, acted as an on and off switch. Because all you need for electronics is 2 states for logic, an on and off state. And you can link those together into all sorts of logic gates, and that's what basically your computer chip does. So, as I said, computers moved on a bit from there, and they moved to use something called a transistor. A transistor is what's called a transfer resistor. That's where the name comes from. And all it is something that can either switch on a current or switch it off. Just like a little switch, but very carefully done. And there are various ways that you can link these transistors together, either on or off, to make different what are called logic gates, and or gates, nor gates, not gates, and it depends on how these are switched off. The whole of computer language depends on binary numbers. It's very easy, because it's just 2 numbers you have to add together, a 1 and a 0, and it's all powers of 2, and you can see the 1s and the 0s here, and it gives you logic tables, and you can map those logic tables to algebra. It's quite a nice, neat bit of maths. And it's very easy to develop code that works around this. So it was very obvious why they used this method. And all you actually need for a computing system is 2 different states, one representing on and one representing off. That was the first transistor in 1947. William Shockley, John Bardeen, and Walter Brattain built this very, very crude looking transistor. And this was the very first transistor ever produced. This was in 1947 at Bell Labs. Schottky was a very unpleasant character and upset an awful lot of people. And some of the people that worked for him eventually went on to form Intel, that you know about, and Texas Instruments. So he was a father to all of these great Silicon Valley people, but not, I think, a very pleasant person. John Bardeen went on and got himself another Nobel Prize, which is quite cute because you don't often get more than one. But this is really, really basic. If you look at the picture on there, it's basically a slab of metal, a conductor, and then you've got, on top of that, a slab of germanium, which is a semiconductor. And then that's actually plastic, that sort of triangle. And then there were 2 very small gold contacts coming to the point, not quite together, at the point of the triangle. And the idea is you put a backgate on, you put an electric field on through that metal contact, and that makes electrons pass through that semiconductor, which is germanium in this case, and it completes the circuit. And you can switch it on and off from that back gate with nothing moving, nothing getting hot. So this is quite important. We're going from the days of those tubes that got very hot. That's where we were in 1947. What I've got on the other side is a Power 8 CPU, computing unit. There's 5 billion transistors in that unit. It's quite small, it's only 650 square millimeters. It can be run at 4 gigahertz, really fast. It has 15 separate layers of transistors in that, stacked. So you're not only using the flat surface, but you're stacking these. All able to be individually addressed. And it's got 12 processor cores. It's sort of the top of the range, if you like. I'm sort of hoping to get one of those at some point in the future. But that gives you an idea of where we have come in a relatively short amount of time. And I want you to remember that when I start to talk about where we are now with carbon electronics and where I actually think we're going to be in much, much less time than this. So, as I said, electrical conductivity can be manipulated. Semiconductors are very useful. We don't use germanium really now. We use silicon because we can make silicon cheaply and very pure. Silicon is basically, I'm going to show you a little piece of semiconductor silicon, if I can find it. I was trying to be really good. Did I leave it in the box? I'm not entirely sure. I might have it still in my box of goodies. Oh. I'm going to pass this round. This is what silicon chips are made out of. It's basically glass. It's pure n-doped silicon, so this is silicon that is doped so it can carry a current. So that can act as your backgate. And then there's a dielectric layer, which is silicon dioxide, which is glass, sand. It's easy to make. Well, I say it's easy to make. We can make extremely pure silicon now. And we can use semiconductors because they're very easy to switch on and off. They're not like metal. They just need a little sort of tilt, and you can get a current going through, and a little tilt back. They don't use up much power in order to create that switching. And in a sense, computer chips can be thought of as a tiny assault course for electrons. And you might say, well, if silicon's already out there, why would we want to go and look for something else? I've just shown you this fantastic chip, 5 billion transistors all on that chip. And it's certainly true, all of electronics today is dominated by metals and by silicon. And why would we want to change? What would be the driving force that would make us want to change that? Well, this is famous Moore's law. Moore's law is interesting because he's actually been proven to be right. There's an almost exponential growth of how things have shifted and how things have accelerated. If you go from about 8,000 years ago, the caveman came out of his cave and started ploughing fields. You could call that, if you like, the agricultural revolution. About 8,000 years later, you had the Industrial Revolution and you had the steelworks. And then we got, maybe 100 odd years later, we got the light bulb. And then things just took off. Look at the difference between the moon landing and the World Wide Web. I went to CERN earlier this year, and I actually got to see the very first World Wide Web server that if it had been switched off, none of this horrible mess of the World Wide Web would ever have occurred. And look at the difference between the World Wide Web and where the human genome has been sequenced. The power of our understanding that has been driven by the technology. We've got Babbage, a computer. That's electromechanical computer. Babbage's computer was basically a very, very clever adding machine, abacus. where it was all full of dials and cogs and things clicking around, could do some interesting things. The Colossus that I showed you was built out of those little valves that I passed around. And then you've got the Apple. I have a Commodore PET from 1983 with the word star program, all capital letters, because it couldn't cope with any more than capital letters. And it's completely in working order. It's my pride and joy. So I only ever put it on every so often, and it's kept hermetically sealed in a large box. You've got, do you remember the Pentiums? 386, 486. Then everyone wanted a Pentium. And then everyone wants an i7 chip. And I obviously now want one of these new computing chips. What's interesting is where we're going from here onwards. Because if we carry on growing at the rate we're going, very shortly we are going to overtake what the human brain is capable of doing. And probably in about, say, 40, 50 years, you will probably have computers which will have the computing power of all the brains in all the world. And that is actually a very difficult concept for us to understand. And we've probably overstepped, I don't know, that's a philosophical thought. Now, I talked about silicon. Silicon has huge amounts of money invested in it. So if we want to move from silicon to another technology, it's got to be much, much, much better. What they call disruptive technologies, silicon taking over from the valve, for example, means you've got to throw out the whole paradigm of how you do things, throw out all of the investment in these great big clean rooms. This is an example of a big semiconductor clean room. All of that will fall by the wayside. You'd have to reinvent the way that you... And so it's not likely to happen very quickly because there's billions of pounds in money put into this. So when you read in New Scientist or in the Daily Mail or wherever it is that graphene's suddenly going to overtake everything, it probably isn't. It's got to perform better, it's got to be cheap, and it's got to be reliable. And when you start to think forward, very often the first applications have got to link into with the technology as it exists now. It's got to be something that will integrate into a silicon technology. And so why am I interested in carbon? Why is it special? It's special because it has some unique chemical properties. Carbon is unusual because it sits in a certain place in the periodic table. It's not a metal and it's not a gas. It sits in a place in the periodic table where it doesn't want to lose electrons, it doesn't want to gain electrons, it wants to just happily share electrons with other carbons and other atoms. And carbon likes to bond to itself. It bonds to itself in, as you can see up here, a variety of rather interesting ways. And it depends on how the electrons in these different, what are called allotropies of carbon, bond as to the physical form of that carbon material. Electrons in atoms, and I suppose atoms. How many people have seen this picture in GCSE textbooks? There are quite a few. They're lying to you. They're lying to you terribly, terribly. You've been totally misled. This is a great cartoon, and totally like it isn't at all. For a start, the nucleus of an atom is like a pea or a grain of rice inside a football stadium in comparison to where the electrons are sitting. It is intense, intense positive charge. The electrons do not whiz round in these wonderful sort of orbits here. They actually sit as probability densities. So you have to understand a bit about quantum mechanics, but you can visualize this beautifully, and you can actually map out those probability densities of where the electron's actually going to sit. And because of that, It allows you to understand why graphite, for example, forms bonds like this, carbon bonds like this to form a diamond structure. And they bond together, forming what's called covalent bonds. So two electrons basically share a strong bond. They overlap, these two electron probabilities overlap, so there's a lot of probability where the two things overlap. That's all the quantum mechanics I'm going to do for today. So in fact, all of chemistry, even though I'm a chemist, I will be honest, all of chemistry is actually the physics of an electron, or electrons in systems. It isn't smelly tubes of smelly stuff. Where does carbon fit? Now I've got a picture here of the periodic table. I'm going to tell you to ignore all these ones in sort of pale yellow sitting in the middle. So the scandium, titanium, vanadium, chrome, manganese, all the rest of it. They're transition metals. They sit in another block called the D block we don't need to worry about, because we just need to look at the top row. So that, if you imagine bringing those top rows together, carbon sits, it's got an atomic number of 6, and it sits in the center of that top row. If elements sit over that side, over on this side, with lithium, sodium, potassium, beryllium, magnesium, over that side, they desperately want to get rid of an electron, because they really want to be like the little blue ones out at the end, right out over on that right-hand side, which are called the noble gases. They have electrons configured in such a nice, energy-sensible way that they really don't want to lose or gain electrons, so they don't bond with anything, even themselves. So things like helium go around as just one helium atom. Hydrogen, on the other hand, desperately wants to get rid of electrons. Lithium, potassium, they want to get rid of electrons. But carbon sits in the middle of that, and it doesn't. And it isn't a metal either. Now, it's quite interesting because we talked about silicon. If we look here, we've got carbon all in the same row going down, or all in the same column going down. Carbon, silicon, germanium. Silicon and germanium do have some electronic properties that are reminiscent of carbon. What they don't have is the behavior of carbon, because they've got lots of electrons between the electrons that are orbiting, that do the chemistry on the outside, and that little tiny nucleus in the middle. That makes a difference. Heavy elements at the bottom. So why is bonding important? Well, because carbon's unusual in that I talked about electrons. Well, the electrons sit in what are called orbitals. And those orbitals are very close in energy for the 2s and the 2p orbitals. So these, if you like, probability densities sit very close in energy, which means it's more favourable for them to form a bond and hybridize than for them to sit by themselves as separate sort of energy levels. And the different forms of hybridization, in other words, different ways that they can hybridize, affect their electronic character. So, this is carbon, and it hybridizes in a beautiful what's called tetrahedral arrangement. So one carbon is attached to 4 other carbons. It's incredibly strong. It's a molecular crystal, and you know that carbon is, diamond is one of the strongest materials around. What I have here is another way it can bond, and that's by 2 of the p orbitals and the s orbitals overlapping and sharing density and forming these molecular bonds. But one of the p orbitals is left free, and it's a slightly higher energy, and that sits above and below the plane, that orbital. And that can hold an electron. That's what makes this interesting. This is graphite. I'm going to pass around some graphite. I shall have to collect all the things I'm passing around in a minute. But here's some graphite. This is my mucky graphite. This is a beautiful and very, very precious sample of graphite. So if you'd like to pass it around. First of all, the interesting thing is you'll see it's shiny. That has quite an interesting, it's shiny because of the electron behavior on a graphitic surface. It's black as well. And that brings me back to my original thing about carbon being black. Graphite is planes like sheets of paper. They're very weakly bound between the planes. This is what they call van der Waals bonding. It's very weak bonding, which means you can cleave off planes. Every time you write with a pencil, you leave a trace of graphite behind you. And for a long time, we knew carbon as graphite, we knew carbon as diamond, we knew carbon as soot, sort of amorphous diamond, but there's a whole family. So we've got diamond structure there, we've got the graphite that I talked about. There's Lons Delight there. You've got cage structures. These are the Fullerenes that I'll talk about in a minute. You've got amorphous carbon, which is just basically soot. My husband thinks this is all soot anyway. And you've got these beautiful nanotubes. Now I'm going to start off talking about Fullerenes. Now this is an absolutely fascinating story. This is Harry Kroto. And he was one of the Nobel Prize winners for discovering Fullerenes. But it's a weirdest story as to how they were discovered. They were not in the least bit interested in chemistry here. They were interested in chemistry deep in molecular clouds that sit between stars in cold areas of the universe and the galaxy. And these stellar dust clouds, they can do infrared and radio spectroscopy on. And they kept getting this signal for a stable carbon molecule that had to have 60 carbons in it. And it was doing their heads in because they were not sure what was happening. They weren't sure of their data. So they decided, well, we can't go out there and sample outer space. We'll go and try and create this for ourselves. So, and I've done this experiment as well, and I'm quite happy to share the slides of doing it. What you basically need is a large welder, 2 carbon rods, some balloon helium, and a milking machine pump, if you want to do it my way. They did it slightly in a nicer way, but that's essentially what they did. They took 2 carbon rods, and they put an arc across them to create carbon plasma. So all the carbon atoms are floating around, and they coalesce. This is what's happening in the universe, and then they thought they'd have a look at what they had and, you know, pin this down. And they got this C60 coming up again and again and again. And this is a C60. It took them ages to work out how these 60 atoms could possibly fit together. And as you can probably see, it's actually molecular football. It's actually hexagons, and every so often you have a pentagon. The pentagon allows you to curve things in. But if you look at every single carbon atom, each one is bonded to 3 other carbon atoms. So it looks a bit like the structure you've got when you're looking at graphite. So this is sp2 bonded, which means the whole surface of this have these delocalized electrons buzzing over the surface. So this is quite electronically rather interesting. One of the things that they've done with Fullerenes is that they've used them a lot in solar cells, but they've used them in bulk. They haven't taken, although you see these very beautiful pictures, and you'll see these in magazines and New Scientist or wherever, these systems, these are cartoons in some way. They're bulk systems, but they're very, very useful in solar cell applications and for some electronic applications because of the way the electrons can be perturbed. You can actually do chemistry on here and you can put chemical groups on here, and as you can see, stitch them along, in this case, polymer, a conductive polymer. In 1996, they got the Nobel Prize for discovering fullerenes. I'm not going to talk hugely about fullerenes, but I did want to sort of mention it. I wanted to talk a little bit more about nanotubes because that's slightly more developed in lots of ways. Nanotubes are beautiful, and I remember getting highly, highly excited by nanotubes. And one of my PhD supervisors many years ago said to me, well, there's no point. He said, how are you going to solder each end of it? How are you going to make something with a nanotube? We can do it now. This is that silicon that I showed you. So this is the N-doped silicon. This is a silicon dioxide layer. Here's two little electrodes here, what are called the source and the drain electrodes. And running across here in red, although it's not really red, but it's just a sort of false colour image, is one single nanotube. Now, a nanotube looks fantastic if you look at it like this. There's a whole variety of different forms of nanotube, which I'll talk about in a minute. But if you imagine it like this, you can see if these are all covered with a layer of electron density, delocalized electrons, it can be like a giant molecular wire. And this could be really interesting. So people got really excited. Easy to grow. You put down a catalyst of iron oxide, and you can grow. You get a plasma of carbon atoms, and you can grow these things up at huge length. And so this is what they call a nanotube forest here. And you can do incredibly exciting things because you can actually take a slightly bigger nanotube than this one and put fullerenes inside, and these are called p-pod structures. So this is an example of a p-pod structure. The reality is, and this is what you've got to understand, this is fantastic, almost science fiction, and you can do this, and you can do it in the lab and you can quantify it. That's what carbon nanotubes really look like. If I go to Aldrich and I order my carbon nanotubes, I do not get these beautiful little sort of thin tubes that I can pick out one at a time. I get a great pile of soot. And this is the problem, and it contains all sorts of nanotubes. Here's another example, which is an absolutely beautiful example. This is IBM, their Watson Research Center in New York, does a lot of fundamental physics, and they're particularly interested in nanotubes, fantastic electronic properties. You can have them completely conducting. Depending on the way that they're put together, you can have them as semiconducting and even insulating. And they imagine that they could take this nanotube and lie it down and chemically absorb it onto a semiconductor. And this was absolutely fantastic. But this is a picture. You tried doing that in the lab. I can assure you it's not that simple. Nanotubes all in a tangle is how I describe it. Nanotubes' behavior depends on the termination. This termination on this nanotube is what's called zigzag. It's zigzag, 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 zigzag. This nanotube, if it was long and a real nanotube, would be conducting. If I have an armchair, well, you can see it's quite different. You're going cross, up, cross, down, cross. It's what's called armchair. That behaves very differently. They also can have a certain twist to them, what's called a chirality. They can twist the way that they've actually bound together. Depending on the diameter, the chemical properties of these nanotubes are different. The reality is that nanotubes actually like each other. And so if I have nanotubes, they all want to stick to one another. They all like each other's surface because they're all delocalized electrons, what's called aromatic, and they like to sit next to one another and conglomerate in great big piles of soot. So on paper they look fantastic, And huge amounts of theoretical work show that they should be brilliant, but we have to separate out the individual types of nanotube into conducting, semiconducting, insulating. They're all going to be different lengths, okay? Then we've got to be able to pick that nanotube up and carefully deposit it where we want it to make our 5 billion transistors to compete with silicon technology. So why are we being bothered? I can tell you why we're being bothered, is that there's a limit to how many transistors you can put on the system. And we're almost there. That you get so small that what's called gates start to talk to one another. And therefore you don't get fidelity, you get interference. It doesn't behave quite as you're expecting. You're down to the quantum level. It's really hard to be able to deal with things like that. It has been done. However, you can use a solution of nanotubes as a nanotube ink, which is very conducting because they all sit one on top of another, and it's really quite useful, and they are used. So we've got a sort of, if you like, rather like when I talked about Feynman, we're not really using it to its full potential, but we're sort of making the first steps. So we're sort of still playing at it. We haven't really exploited it as far as it can go. Now we come to the wonder material, namely graphene. Graphene is a sort of mother, if you like, of the materials, examples that I've given you of nanotubes and fullerenes. If I take a stack of these sp2 layers, one on top of the other, I've got graphite. If I peel just one layer off, I've got 1 atom thick. Carbon also is very, very light. Now, I'm saying you're using silicon, which is heavier than carbon. You're using metals in electronics, very heavy. Lightweight might be important. We don't know. A sheet of graphene also is a polymer. It's a carbon polymer. You can bend it and you can stretch it and you can make it into interesting shapes. You can't do that with a piece of silicon. You've seen that silicon, it's glass. You try bending glass and it snaps, so it's not really very useful. Carbon's relatively cheap. I can find all sorts of sources of carbon, and people have. In fact, we make graphene now using carbon sources. This is an interesting image because it just is quite reassuring when people do AFM images. This is atomic force microscopy. And you're basically able to see this beautiful honeycomb shape. You're seeing it down to the atomic level. It's electrically conductive. It's one layer thick of this, although graphite is black, one layer thick of this is pretty transparent. So you've got a transparent conductive film. This is starting to get really exciting. The electrons in here, I can't explain really at this level quite how exciting they are, except to say that they are actually relativistic Dirac fermions. They behave like light. They behave in a completely different way than electrons do in other materials. These electrons go across here in waves. If this was perfect graphene, if I had one perfect layer that was absolutely perfect, they would travel what's called ballistically. They'd be relativistic. They'd be traveling at a huge what's called Fermi velocity. So really interesting electronically. So it's hardly surprising that all the physicists get hold of this stuff and think, my God, this is amazing stuff. We've got to do something with it. So we've got from this graphite, and I don't know where my bit of graphite is, but from the graphite, you can peel off a single layer. And I'm going to in a minute. Please be very careful with these. Not that these are samples that we're going to use again, but I don't want them sort of dropped on the floor. These are what are called packages, and they're where we do our basic understanding of the science. These are little tiny electronic boxes that you can sit your graphene in and make little tiny contacts to that graphene and do electronics on it and understand what happens to the electrons when they're passing across that one atom thick layer. And this was a great photo because it's the only time I've ever been able to celebrate a Nobel Prize with somebody. That was Kostya down at the bottom. We got drunk on Armenian brandy, but that's besides the point. They won the Nobel Prize basically, and if you want to hand these round, be careful with them as they come round. There we go. They won the Nobel Prize for understanding some of the really basic physics of graphene and just having the audacity to try. They never believed you could get one atom thick. Everybody, it's a paradigm. Nature doesn't like 2 dimensions, so therefore nature, you never find 2 dimensions in nature. And lots of people had played with graphite and got down to some very, very, thin graphite and never carried on doing it. But Kostya and Andrei Geim did. They carried on, and then they had the most wonderful bit of good fortune. And I'm hoping that they were able to see one atom thick. Do you remember I passed around, and somewhere going around is that silicon wafer? It has a very tiny layer, a few hundred nanometers, of silicon dioxide sitting on top. Now, this is a physicsy thing, but it's quite easy to explain. You've all seen what happens when you've got a very, very tiny, thin layer of oil on water, and you get an interference effect and rainbows. Well, if you get a very, very tiny, thin piece of graphene and put it down on a silicon dioxide surface, providing it's just the right thickness, about 300 nanometers usually does quite nicely, you get an effect called the Fabro-Perot effect, which is an interference effect, which does allow you to see one atom thick, but only just, and it works well in green light as well. So if you look at this one in the corner here, you notice how tiny these little tiny bits of graphite are, because we've just peeled them off a lump of graphite, and so these graphene pieces are tiny. You can see that very faint one where it says 1L, that's one layer. You're looking at one layer thick. I'm going to show you something at the end I think you'll find absolutely amazing. But actually, where you're looking at those little packages, you'll see what people are actually working with. They basically get a piece of graphite, they get a piece of sellotape, they put the graphite on the sellotape, they peel it off, and you're peeling off some, and then they peel it and peel it, they press it down onto silicon, and then they spend hours looking down a microscope to see if they've got any nice one atom thick pieces. And then you find it, and then you map it out on your tiny little bit of silicon, and then you get your you put down PMMA, which is photoresist, and you get your and to be honest, it is so laborious, but you're able to actually connect up these one layer thick. Why bother with that? Isn't it really ridiculous? Well, no, because nature makes beautiful crystals. And graphene isn't completely perfect either, because we're using graphene, and we're using graphene on the outside world. So all the theorists can do all their beautiful theory with graphene, and then we take it out into the big wide world. We're sat in here, you're breathing, aren't you? Lots of water vapour around. People got scent on, people got BO next to you. We have lots of organic molecules knocking around in the atmosphere. They all like to land on that graphene surface and wreck your beautiful electronics, because if something sat on the surface, wallop, it's going to stop those electrons moving quite the way you expect to. And actually, some of the work that I did a few years ago was actually trying to really understand what was happening when molecules came down onto graphene. Even though I've said all of that, it's only 11 years since Kostya, Novoselov, and Andrei Geim first isolated that graphene sheet. We can do clever things with graphene though. Now, this is work that's been done in Exeter, and what they've done is they've taken the graphene sheets, and you've got all these spare electrons sitting on the top. Why don't we do some chemistry with them? We can fluorinate it, put fluorine atoms here. So you're, in a sense, creating a single layer, if I can get rid of the top bit here, a single layer of puckered what's called sp3 carbon atoms, and you've saturated all of those electrons by making them bind with the electron that fluorine just loves to give away, because fluorine's, you know, that wants to get an electron, and so you can get fluoride when you break up fluorine molecules, and that will bind and saturate and use up all of those electrons. So none of those electrons are free to carry a current. This is insulating. It's a very nice insulating process. But we can use something called an electron beam, which is literally a beam of electrons that we can fire in a very, very tiny, tiny, tiny pattern, down to nanometers, and we can carve out circuits. So wherever we've removed those fluorines, we're back to that graphene that carries a current. So you can carve out circuits on the nanometer scale, on the almost atomic scale, which is very exciting. Then, now this goes back to things that I did many years ago, because I started out as a chemist. This is a chemist getting you. What's interesting is graphene, because of the way it is, it's like a metal. It hasn't got a gap. In other words, it's not like a semiconductor. And sometimes you might want to use something that has a gap, and if you get a very thin ribbon of graphene, it behaves more like a semiconductor. And also you can create these graphene wires. And this is doing it chemically. It's using big chemical, big aromatic groups, stitching them together and producing these extended sort of polymers. But they are beautiful, and they're all, as you can see, it looks under the AFM exactly like it looks in the pictures that they've drawn, which is always very reassuring. But also look at what you're getting. It's the same problem that you've got with nanotubes. You've got all sorts of things in there. We might be able to isolate one or two of these and do some electronics on it, but there's all sorts of lengths of chain. There's all sorts of ways that they've joined together, and it's not reproducible. So we can do some fantastically clever things by doing the bottom-up approach. What's a catch? Also, what's a catch is I've tried to do some chemistry with big molecules. They are brick dust. You cannot get them to dissolve in anything. I mean, you have to really work to do that chemistry. So it's not easy chemistry that I've just shown you. That is really difficult chemistry in itself. And you get a mixture of different products, and in the centre is a bulk product, soot. Sorry, I'm coming back to soot here. My husband had it right. It's all soot. Okay. But life does it. You're all sat here. You are predominantly carbon systems. Your life builds all its scaffolds, all its proteins out of carbon. There might be oxygen, there might be a bit of nitrogen, there's going to be some hydrogen in there, but essentially you are a carbon system, because carbon can form so many different bonds to so many different things very stably. The other thing is that life depends on electron transfer, miniature electronics. Carbon is very important in creating environments that allow that miniature electronics to occur. So nature in some ways has solved our problem of making things tiny. You eat your food, you eat your dinner, and you burn that, and your body in the process goes through a process called oxidative phosphorylation. Anybody doing biology will know what I'm talking about, but basically it's a little electron transfer chain where electrons get skipped between different proteins. And those electrons get skipped between those proteins at exactly defined voltages. And very interestingly, there's also some evidence that there's a quantum mechanical property of electrons called spin. Electrons, I didn't talk about this, but they can live in a state of spin up and spin down. Don't need to understand what that is as such. You can imagine it as spinning tops if you want to, but it doesn't really help. But nature can see that spin, and it helps it shuffle the electron. But the greatest computer we have so far is our brain, and that is based on carbon. So evolution over 3 billion years has allowed us to do that. A beautiful example of this is photosynthesis. This is where we're using the splitting of water and the absorption of light to split that water as a first step in an electron to release electrons down an electron transfer chain. Plant life supports everything. Although you might not be vegetarian and hate your greens, you know, the cow that you're eating when you're eating your steak has eaten the greens for you. We all depend on and those people who've done biology will recognise there as a nice little plant cell, and inside a plant cell you have little green sort of sacs of pigment, and those green sacs of pigment are in fact, if you like, the photosynthers. They are able, those pigments, the chlorophyll, that green pigment, is able to pick up the energy from light, transfer it into, and kick into electron energy, an energy that can split water that releases electrons that pass down a chain. And I'm not going to go into huge detail on this. I've put a few things in here. But basically the first process is splitting water. We'd love to split water. If we could split water like plants do, we'd all be driving hydrogen cars. But at the moment we can't do that. And then you release the electrons, and that little electron gets shuttled through several proteins. And then finally, at the end of all of that, it meets NADP and a hydrogen, and they gain an electron, and it puts it back together, and this is a reductant. So the electrons are trapped and stored in those molecules, which is very useful for the body. Part of this process liberates hydrogen ions, and you build up a big concentration on the inside that can be pumped through, just through osmotic, through diffusion gradients, and that turns a little machine that makes ATP. ATP is what the plant and you and most of biology depends on as a convenient energy source. So nature's very, very clever, and this is all at the molecular level. But we can do clever things with molecules. This is IBM's single molecule logic switch. Notice it's a picture because they haven't really got a real one that looks like that quite. But they think that they can make logic gates using single molecules by designing the molecules in such a way that you can allow electron transfer and changes in conformation of molecules, for example, that change the electronic properties and switch molecules on and off. You need two states, as I said, for all electronics, a 1 and a 0. And in fact, this is a book that's recently been published, which is molecular logic-based computation, where a lot of the, if you like, the background work that's going to be needed to make this work is being done. This is an interesting example. This is supposed to represent two gold tips, and you trap a little molecule in between. And the molecule gets trapped, and if it gets stretched a bit, it changes its electronic properties. And you can use that as a way. This is University of Columbia's work, so this is not stuff we've done. There's an example of where you've got a conformational change, changing the electronic properties. There's been a lot of work published looking at whether we can use DNA as a form of logic gate and DNA computing. You might have sort of come across that in New Scientist. But essentially, up at the top is the basic idea. You've got the logic gates that are basically different electronic forms of different molecules that can be modulated in some way, usually through light. So a lot of these depend on light reactions, like nature does itself. Challenges: material purity, absolutely vital. You've just seen most of it is soot. I depend, if I'm going to, originally when we made graphene, on whatever came out from when I squashed that bit of sellotape down on the piece of silicon dioxide. And there were chunks of coal there. Only every so often would you see something that you thought might be a single layer. Device fabrication on that level, we can go down to down to nanometer resolution now. So that's becoming possible. The reproducibility and scale up is much more difficult. I had a small son who, when he was about 6, came into my lab and he said, "I've thought about it all," he said. "What you need is little Chinese ladies to knit you graphene." You've had all these old ladies merrily knitting graphene for us. We can't quite do that, but I'm going to show you that we're sort of on the way to doing it. You need very small knitting needles as well. However, we've got high performance. We know how it can electrically behave, and it is fantastically interesting. We've got flexibility, we've got transparency, I haven't got any slides here, but we make a material that one day I expect will overtake indium tin oxide for producing coatings on glass, which is called graphexeter, which another colleague I think spoke about in a previous talk. You've got to make them link into the current technology, but there's a lot of work being done on graphene inks and nanotube inks. And in fact, I worked with some students last year and we were making graphene inks. That looks really interesting. The true, if you like life, molecular electronics is further away. So I've talked about lots of things. I wanted to look forward to, I wanted to look at what nature does and see if we can understand really what true molecular electronics is about. And that's about shifting electrons in such a controllable way that we can do all sorts of clever things with them, much more in the way that life does. And they're very big questions. It's going to take years. I don't think it's going to be overnight. I think it will happen. It'll be clever people like you who are much brighter and less old than I am, who start to work on this. So my view is that carbon electronics is the future black. It's definitely not. But you've got to remember what people are really dealing with, and they're not dealing with the beautiful pictures that you see in the Daily Mail. They are dealing with reality. Would you like to show I just want to show you a little picture from our lab by Saverio Russo, and I'd like you to if you would like to, we're swooping in on a little tiny chip of silicon dioxide, and you're seeing some gold contacts that we've put on, and watch the scale on here. That is 1 atom thick. And they're gold contacts. So you're actually seeing something, an atom thick. Do you want to run it again? So we're coming in, we're coming in, we're coming in, we're coming in. Look at the scale, 40 microns, 20 microns, 10 microns, 5 microns, 4 microns, 3 microns, 2 microns, 1 micron. Nanometer scale, so we've got down to 500 nanometers. So you can do it. We can do fantastically exciting physics. That's the reason why people turn up to work in the morning. but I think you need to be realistic. Go and look where we've come from. Those valves that I handed out, chips as they are now, and you need to be realistic, but I think given another 10 to 15 years, you'll find that we want to turn to molecules because we can no longer do what we want to do using the technologies that we currently have. Okay. Has anybody got any questions? And can I please have all my bits of stuff back? That's great, thank you. That's
Any
lovely,
questions,
thank
and
you.
I'll get them on the mic.
I'm getting it all back, slowly, bit by bit.
Thank you. Yes, graphene, the uses all sound wonderful. And I've got a friend actually doing chemistry who's doing exactly this topic at the moment, and he's so excited about graphene. But I often say to him, with so many of the great scientific discoveries of the past, as well as wonderful uses, they also, more sinister uses eventually come to appear. Do you think that will happen with graphene? Will there come a day when it is used for far more sinister purposes?
It's quite interesting because certainly nanotubes are not entirely innocent. They're actually quite toxic and they can do quite a lot of damage. The toxicology of nanotubes is now something that's worrying people because we haven't really thought about the fact that we've got these long, thin molecules, very, very extended molecules that our body can't handle. In regards to graphene, I think it's more to do with the thing that I mentioned earlier on, the fact that we're developing computing techniques even now that are surpassing what we're capable of in a huge way. And there's a lot of debates about if we've got these computers that are orders of magnitude more powerful than the ones we have today, whether they will the great HAL whatever paradigm, or and we're going to be run by computers. I would probably say we probably are already. I don't think there's sinister uses. I think that we will find that the things that make money first are going to be the low-hanging fruit, the things to do with carbon inks, nanotube and graphene inks, the things to do with replacing ITO. We can actually make graphene now on large scale using chemical vapor deposition. It's not so good as a graphene that we make, that we can exfoliate. So it's not got that quality, but it's good enough. And to be honest, most technologies look for things that are good enough. They don't necessarily, it depends what you want to use a graphene for.
Any other questions?
Hi. When you were talking about the fullerene, you mentioned the solar cell application. So when graphene was advertised as being a miracle sort of material, they said that graphene could be used in solar cell applications. But what I was wondering, is it just in the fullerene sort of configuration that they were referring to?
No, you can use graphene as, when you build a solar cell, you need a conducting layer as part of that assembly. Mm-hmm. And graphene looks like it would make a very good, extremely thin, extremely transparent material, and it's also flexible. Mm-hmm. So solar cells have improved immensely in the last sort of 5 or 6 years, but the efficiency still doesn't come anywhere near the efficiency that Mother Nature does. Right. So looking for new materials is always going to be something that's of interest.
So at the current moment, the most that they were able to get the efficiency of solar panels was something like 40%.
Yeah.
But if you use graphene, they promise something like 60 to 75%.
Possibly.
How by using graphene is that obtained?
It's basically because you've got a very, very conductive layer, and it's by being able, I think the big thing is by being able to, most solar cells are built of stacks, essentially. So they're not just graphene, it would be graphene It might be some other material sitting on top that did the light harvesting and then passing it through to the graphene. And because it's all surface, this is an interesting thing when you think about it, which I didn't really sort of talk about, but graphene, if you look at it, if you imagine one sheet of this, every side of this is all surface. Whereas in most applications, you're dealing with something with bulk, so you're only conducting over the... And so this makes these sorts of materials interesting for that, interesting for sensor applications as well, for the same sort of reasons. You're dealing with something that's all a surface effect. So electrons in graphene are interesting and they're different. And it makes it efficient because you've got a very close and intimate link between where you're generating and harvesting energy, essentially.
I also just had one more question. In terms of when you said you can use the electron beam to, I think it was to deposit the fluorine to make circuits.
Yeah.
Is that essentially like replacing the copper tracks with the electron beams to make it conductive?
What you're basically doing, you imagine a whole surface and it's all insulating because every one of the electrons that you've got in graphene have been stolen by these fluorines that are bound, so that they're bound up in a chemical bond. If you put enough energy in with an electron beam, you can break that chemical bond and basically pull off those fluorines. And if you can carve out very, very small, thin pathways, you can imagine that you could use the electron beam to write circuits by removing and allowing a conductive pathway of pure graphene in between insulating areas of fluorinated graphene. So that's the idea behind that. Again, it's been shown to work on the lab bench. It hasn't been shown to work on huge scale. So it's rather like going back and looking at that very first transistor that I showed you, which was messy and mucky, and it looked like it was made in somebody's shed, which wasn't quite, but almost. But the idea was there, and they could show a proof of principle, and a great deal. It's not the place for academics at university to make the all bells and all whistles commercial product. That's technology. That's what I would call, development technology. At university level, you need to be able to point people in the right direction and say, this is really interesting. It has all of these properties. And so I suppose I'm interested very much at fundamental level on things. I like technology. I'm extremely techy, but I'm actually interested in how things behave at a very, very much more basic fundamental level. And that's the sort of difference between what happens in industry and what happens at university. And we need each other. We can't create what they do in industry. We don't have the money, the capacity. We don't have that, but what you do have at university are people who are thinking very, very fundamentally and coming up with the brand new ideas that then industry takes on.
So you mentioned the different types of nanotubes had different electrical properties.
Yes.
Once they've been fabricated, is it possible to change them between the different states?
No, not in the sense if you've just got the basic nanotube, because once that's all bound together, that's zigzag. I'd have to change and reconnect everything to make it armchair, to make a different sort of termination. So it actually isn't possible to do that. But what we can do, and what you can do, is to use some quite clever techniques to separate out different types of nanotubes, so you can get predominant, and sometimes they form double nanotubes, a nanotube over a nanotube, and this is what they call a single-walled nanotube. What I haven't shown you is you can have multiple walled nanotubes, so it's a tube around a tube, around a tube, around a tube. Again, they've got interesting electrical properties. Once it's made and it's stitched together, unless I'm going to take all of this to pieces, I could take all of this to pieces, and remake it. I should get, if you want to do it and have another couple of beers and sit and remake it, you can make it in a different configuration. That would then represent a different type of nanotube. What you can do with nanotubes as well is you can, because of the way that they're curved, all of those sp2 bonds are a bit stretched and pulled, which means that these are more reactive than graphene. So you can do chemistry on top of them and do some interesting chemistry and do interesting things with nanotubes, but basically it is as it's stitched together, and that's chance. So if I make a lot of nanotubes, I will have all sorts in that collection of nanotubes, and only some of them will have the properties that I want.
Thanks.
That's all right.
I think unless there are any more questions, we'll end it there. But I just want to say, before we all kind of give a round of applause, just as someone who doesn't really know about physics or nanotechnology, it's amazing to see the challenges that the future is going to hold, and to see that actually Exeter's research is kind of contributing to industry, as you say, at that level. So I found it absolutely fascinating. But if we could all put hands together for Dr. Sharon Strawbridge for a really interesting talk. Thank you very much.
Thanks.
And that concludes the lecture. Thank you all so much for coming. We'll have another talk. As you say, there are programs at the back. We have a whole series and a couple more talks. This talk will also be available online on the Exeter Guild website soon, so please check out that and share it with any friends. Thank you very much. Thank you.
Thank you very much. I enjoyed that.